Okay, so good afternoon, everybody. So thank you for being here, the Future Leaders in Robotics and AI, celebrating diversity and innovation seminar series. And this is part of the University of Maryland and Microsoft Robotics and Diversity Initiative, sponsored by Microsoft DC Metro Engineering Site. Now, our second speaker for today is Lidia Al-Zogbi. So she will be talking about autonomous ultrasound-guided robotics to support trauma patients, from diagnostics to hemorrhage control. So Lidia, she's a fourth-year PhD candidate in mechanical engineering at Johns Hopkins University, and she's advised by Dr. Axel Krieger at the Immerse Lab and Laboratory for Computation, Sensing, and Robotics. So prior to that, she received her Master of Science degree in Mechanical Engineering from the University of Maryland College Park in 2019. And the research focuses on developing autonomous medical robotic systems for diagnostics and surgical intervention. So Lidia, the flowers are yours. Thank you.
All right. Thank you so much for the introduction. Let me try to share this. Can you all see my screen? Okay, perfect, beautiful. Do you see the red pointer? That little thing that's hovering. Okay, awesome, cool. So thank you so much for the introduction. I'm super excited to be here. And thank you everybody else for joining this talk. I hope this is gonna be worth your time. So, okay, sorry. So I'm going to give you an outline of what I'm going to be talking about. First, I really want to start by discussing the vision and the challenges for autonomous medical robotics, just to get you a little bit more excited about the field, give you an overview of what we really do before getting into the robotics for supporting trauma patients, where I'll get the chance to discuss the trauma diagnosis and care work that I've been developing as part of my PhD thesis. And then I'll talk a little bit about the future work specifically for that project and my overall research directions and visions that I'm hoping to pursue after I graduate. So, autonomous medical robotics, why do we do what we do? Obviously, people are always going to get sick and people are always going to require medical attention. That's never going to change, but unfortunately, the quality of the healthcare that they're going to actually receive really depends on the provider. And then there's a lot of different items that go in there, like their availability. So the World Health Organization, if you go to their website, you'd notice that some countries have, in terms of numbers, 0.0 physicians available per 1,000 residents of the country. That's a very low number. On top of that, the skills, the experience, the mental and physical state of the provider really influences, again, the quality of the healthcare that they can offer to the patients. Hopkins published a report not that long ago mentioning that the third leading cause of death in the US was actually related to medical malpractice and then clinical errors. So really, in numbers, that actually translates to 250,000 deaths a year that could potentially be prevented with autonomous medical robotics. On top of that, we just came out of the COVID pandemic, or still are coming out of that. And even though COVID introduced new problems, it actually exacerbated already existing problems. So if you had lack of clinicians, that became even worse because everybody was busy assisting COVID patients that needed immediate attention. A lot of people had their treatment and their surgical procedures postponed because of lack of availability of clinicians. Teleoperated robots exist, and it's really nice, but it still cannot mitigate all issues like the skills and experience of the clinician. So really, overall, all of this feeds into an equal access worldwide to reliable healthcare services, which is also going to drive down the costs. We want to enhance patient outcomes and also provide assistance to healthcare providers. So we want to be able to help out both sides of, both sides of people who are involved in this medical procedure. When people talk about autonomous medical robotics, typically everybody just immediately thinks of surgical robotics, but there's actually a lot of other categories encapsulated in this field. So you have diagnostic systems, which just allows clinicians to diagnose the patient. If you look at the far left picture, you can see a CT scanner by Siemens, and even though it doesn't look like a traditional robotic system, it is a robotic system with all its sensing, manipulation, and autonomous capabilities. It interacts with the patient, so it is a robot. For the interventional side of the robots, you obviously have the famous Da Vinci, which, a lot of people are familiar with. It's used for minimally invasive surgeries. But you also have, on the other hand, something called a pill cam, which is a little pill that contains camera that a patient can swallow. And then as the pill traverses the digestive tract, it captures images. And then those images are used by clinicians because it's much cheaper than performing an endoscopy, for example. We have rehabilitation robots, exoskeletons, we have service robots, robots that interact with older people, robots that just move around the hospital, delivering medication or even disinfecting certain areas. So there's a lot going on there, and it's not just surgical robotics. And ultimately, all of that is to assist both the patient and the healthcare provider. So there's a lot of challenges associated with the field. I think the main challenge is that there are just too many of them. Obviously, we need to rely on some form of visual guidance. If you look at the left picture, that's an endoscopic view of a surgery, which is essentially a view of the internal organs of the patient. And that's like an actually really clean picture. You often get blood occlusion, you get tissue occlusion. It's hard to interpret these images. But if you actually want to look at other types of medical imaging like ultrasound, they're even harder to interpret. This is actually a picture of a liver and a kidney. If you really look hard at it, you can see the organs, but it's not easy. And it's, a lot of clinicians still make mistakes because of that. On top of that, a lot of the soft tissues end up deforming. So really all the easy techniques that we could have used to, perform our surgical intervention or other procedures like tracking organs are gone. We can't do any more rigid registration. We can't have any linear assumptions. Ultimately, everything depends on the application and the system. But there are some common limitations like medical imaging system limitations. We can have some latencies. We can have some poor resolution. Patient specificity, how do we make sure that our solutions are generalizable? Decision-making reliability. So all of these are some challenges associated with the field. But in my talk, I'm going to be mainly focusing on the diagnostics and interventional aspect of robotics. And that leads into a good introduction for the work that I'm going to be discussing, which is trauma. What is trauma? Trauma is injuries, basically. In my current work, I'm just focusing on abdominal injuries that could result from a car accident, battlefield wounds, gunshot wounds, stabs, Baltimore. Things happen, unfortunately. It's not that bad. But up to 29% of pre-hospital trauma deaths are actually classified as survivable and were attributed to uncontrolled hemorrhages. And the reason for that is because once the patient gets into an injury, they need to be transported to an ER where the clinicians can perform something called as a fast scan, which is the first diagnostic test performed on the patient to detect any heavy internal bleeding. Now, by the time there's something called the 1 hour golden rule, if the patient is not stabilized within 1 hour, then their chances of surviving drop significantly. So really, by the time the patient gets to the hospital, it becomes too late, and then they could succumb to the hemorrhages. So what we're trying to do is integrate robotics and artificial intelligence when they're really needed the most. So we want to integrate a robotic system in an ambulance, maybe in maybe on an airspace station, maybe in a battlefield, where we do not have well-trained physicians that could assist and then have interventional procedures to mitigate those hemorrhages. And that's basically the need that we're trying to solve. So there are some existing solutions that have been proposed in the past. On the left, you see something called the trauma pod with a Da Vinci robotic system, but really a Da Vinci is not going to make it to the airspace station. So that's a little bit of a far-fetched goal. In the center, you can see a patient-mounted robotic system. Unfortunately, it's also teleoperated, and just looking at it, the workspace is heavily constrained. You're not going to get the chance to visualize a lot of regions. And then what my PI had started working back in 2019 on is a teleoperated robotic system for performing ultrasound scans remotely on a patient. This is a good start, but it's a teleoperated solution. So what we're trying to do is supplement that system with autonomy so that we can perform the diagnosis in the ambulance potentially, or, in the area at the spot of the injury to save people's lives. So the system is a robotic manipulator with a depth camera, a force torque sensor to make sure that we're in contact with the patient, we don't exceed safe limits, and then we have an ultrasound probe to actually collect the ultrasound images. We're running our tests on an ultrasound phantom that we created in-house, actually. It's based on a CT scan of a real patient. So I'll walk you through the workflow of the system. So the clinician would look at a patient and then they can identify immediately where are the regions that they want to scan. We want to be able to translate that level of autonomy to a robotic system. So we began our collaboration with Siemens, where they developed a regression network that takes in as an input a 3D model of a patient body and then returns a set of landmarks. So in our case, the landmarks that we requested were landmarks on the ribcage, because ultrasound signals get completely reflected off the bones, and 3 out of the 4 locations for fast scan are actually for organs that are encapsulated in the ribcage. This research work happened during COVID, so instead of imaging the actual organs that we wanted, we went to imaging the lungs, but really it's still essentially the same concept where we can use the landmarks to avoid bone structures and then determine the volume space that we want to visualize under ultrasound within that ribcage. So we provide target positions inside the ribcage that we want to visualize, and then we develop our own algorithm to identify an optimal probe position and orientation on the patient body so that we can visualize these targets, because the quality of the ultrasound image depends on a lot of factors like the distance of the target from the ultrasound probe, how many layers of soft tissue it's traversing, are we traveling through air? That causes a lot of scattering. So we find the optimal position, we perform all the required transformations, and then we position the ultrasound probe near the target. Now, in an ideal case scenario, we would collect an ultrasound image and look at it to identify whether we're obstructed by the rib or not. We don't have access to that kind of data at the moment, so we decided to develop another algorithm that will allow us to have a better understanding of where the ribs actually are, because the output of the network is not going to be 100% accurate, right? So this is based on the hypothesis that a displacement of the ultrasound probe into the patient body on the rib is going to be smaller for the same amount of force as opposed to the displacement into the body in between the ribs, which makes sense because as the ultrasound probe is in between the ribs, there's more soft tissue. So you're going to be able to go a little bit deeper into the patient for the same amount of force. And really, we showed that it works well in practice, and we've collected some data on that. And then once we identify the larger displacement, we drive the ultrasound probe to that location, collect the ultrasound images, and relay them to the clinician. So this is just a video roughly demonstrating the system. Apologies for the delays between the first 2 videos. My video editing skills are not particularly great, but you can see on the top right, always confused left and right. You can see on the top right graph the force that actually we're seeing, and then on the bottom graph you can see the displacement of the ultrasound probe that we really start recording in between. Like we detect when the force has started increasing, and then once we reach 20 newtons, we record the position of the ultrasound probe and we can get the displacement. You can very clearly see that there's a significant difference for the displacement when you're on the ribs and in between the ribs. So when we're in between the ribs, we're getting at a larger displacement, which here is about 14 millimeters. And so after we identify the location that we are safe to go to for collecting the ultrasound images, we just drive the ultrasound probe and then we collect the ultrasound data and relay that to the clinician. We conducted 24 experiments on a single phantom. Unfortunately, that's all we got. Because it's hard to actually get the phantom. These take quite a bit of time to make. But out of the 24 experiments, when we used force feedback, we got 3 good quality images that were not obstructed by the ribs, as opposed to having 10 out of 24 images, for cases where we did not use force feedback and just simply relied on the landmarks that were returned by the deep learning algorithm. So after we do the diagnostics part, we relay the information to the doctor. Doctor says, okay, this is really bad. We need to stabilize the patient. One way of doing that is to do something called the Ribcage catheter insertion. And it's essentially this catheter, which is a flexible tube that goes through the femoral artery into the main aorta, where you inflate the balloon to constrict the blood flow through the main aorta. So the first step for performing the Reboa insertion requires to identify the correct needle entry point, which has to be between the inguinal ligament and the femoral artery bifurcation, which the clinician needs to identify under ultrasound. So the clinician needs to have an ultrasound probe in one hand, collect ultrasound images, process the ultrasound images, do the spatial transformations in its head, and then get a needle, and then under ultrasound, perform the right needle insertion, make sure we don't puncture through the artery, and look at the images in front of them, after that, they can insert the guide wire and the catheter. It's very complicated task, which is why the Reboa insertion is not commonly performed. So we developed a robotic system that goes on to the manipulator, where we have an ultrasound probe that can be separately controlled. And then we have a needle insertion mechanism with a curved rail that allows us to control the angle of the needle, and then a linear stage to allow us to do the needle insertion under ultrasound guidance. So this robotic system takes advantage of what's called the remote center of motion. And that's essentially to make sure that the needle tip will always fall within that remote center of motion so that we can visualize it under ultrasound. The workflow is very similar to the diagnostics part. You need to feed in a patient 3D model to the network to identify a set of landmarks that we use to guide the robot to the original scanning location. Obviously, using the point cloud, we can identify the normals so that we're always perpendicular. And then because we don't have an actual phantom, we're running experiments on a vascular slab. So the robot will go collect ultrasound images. We have an algorithm for detecting the needle optimal entry point and angle. And then the robot performs the needle insertion execution under ultrasound supervision. And at the very end, the clinician would manually insert the guide wire, but we would guide them as to how deep the guide wire needs to go based on the landmarks that were outputted by the network. So just a very quick video of what the ultrasound images actually look like. This is the robot scanning the phantom, and then you can see the ultrasound on the left side. You can see the arteries. We have a separate algorithm network that we train to get this data, and then I post-process that to make sure that they fit a circle because they look circular. And then just to show you the overall system, the way it works, that's the robot. It's going to go to home position. Then it's going to go to the phantom. We collect the ultrasound images. We process the ultrasound images. Robot thinks a little bit, identifies the optimal needle entry point. We move back to the location. And then if you look on the right side, you would notice that there's the needle insertion mechanism that's actuated. And then in the ultrasound image, you will notice this tiny little needle that you see that is going all the way into the artery. Looks roughly in the center. These yellow arrows are essentially to demonstrate that it's within the blood vessel. So this is roughly what the system looks like. So right now we're in the process of trying to get phantoms so that we can test the algorithm a little bit better, because we can move around this lab and it works relatively fine. But currently, this is the stage where we are at now. Due to time limitations, I can't really talk about a lot of things that go in there, but we have a skin segmentation algorithm that we use, a phantom that was created for the experiments, and all of those were integrated into the workflow for the autonomous diagnostic system. For the actual therapeutic system, we developed a semi-autonomous robot at the beginning, whereby from the ultrasound images that we're collecting, we do the segmentation, but we also do a 3D reconstruction of the femoral artery that we display to the clinician, and then they can select the actual needle entry point, depth, and then angle. And then we extended that work to have our own algorithm for developing the autonomous system. Both of these have still manuscripts in preparation. And obviously for future work, we're still trying to mitigate a lot of other factors that will be really important in a clinical setting, like the vibrations and the patient breathing, patient movement, right? If the patient has shifted during the procedure, we want to make sure that we're still inserting the needle in the right spot, or we're imaging the right ultrasound data. We're trying to get clinical ultrasound images instead of just relying on phantoms, potential animal experiments for the therapeutic needle insertion, and then an enhanced robot design, because right now this is really bulky and we're not going to have a robot manipulator in a real life scenario. But still work in progress, things that we're looking at. And then overall personal long-term research directions that are tangentially related to my work on the trauma robot, collaborative autonomous medical robotics. You've seen that the clinician needs to insert a guide wire through the back of the needle while the robot is there. I'm also interested in collaboration between robots and surgeons in an actual surgical scene. So we need to understand the surgical scene, action analysis, risk-free decision-making. We need to adapt to new environments. Patients are going to change. Some surgeries are going to be more dirty than others. We need to optimize behavior for surgeons' comfort such that the robot doesn't really come in the way. On top of that, things that I unfortunately did not get the chance to explore during my PhD thesis, but I would really love to, is motion planning. So I have a large range of motion, especially for the robotic arm. I need to move across the patient from one side to the other. So it's really important to figure out how we want to, do collision avoidance in dynamic environments, optimal performance and time, questions that are really important to solve when it really comes to deploying the system in an actual clinical setting. And then medical imaging modalities fusion. I've worked with CT data, I've worked with ultrasound data, and it's always been a problem to register the two with respect to each other. And it's also hard, well, soft tissues are also deforming, so that adds a little bit of a complexity there. Extracting and selecting the relevant features, intuitive visualization and usage of the data, how we want to process all that information into something that's going to improve the outcome of the procedure rather than just, adding more data without any actual benefits. Acknowledgement slides. These are all the people that have helped me directly make this work possible. None of that would have been possible without them. Thank you all so much. It's really amazing, the work that we were able to achieve together. Some additional references that are out there that I think are not on previous slides. And thank you for listening to my talk. If you have any questions, please feel free to email me. If I don't respond within a day, please send a reminder. But I'll be more than happy to take some questions, guys. Thank you so much for listening.
Thank you, Lidia. Thank you so much. So yeah, we have a few questions in the chat. So in chronological order. So how do you do the denoising for these ultrasonic images? It seems to me that there is a lot of noise in these images. I think this questions was asked right at the beginning of your presentation.
Yeah, I can see that here. Yeah, so I do not actually denoise these ultrasound images because the arteries, so I only have ultrasound images of the vascular phantom that you've seen. The arteries are very visible. The network does everything on its own. I don't even have to worry about that. This is absolutely not something that could be extended into a real life scenario. So it's definitely a real problem that would need to be taken care of. But when I collect ultrasound images on the diagnostic system and relay that to the clinician, I don't denoise them because this is the usual data that clinicians see in front of them. And then for the segmentation of the vascular phantom, the vasculature is clear enough for me not to need to add any extra pre-processing steps before feeding the data into the network.
Okay, thank you. So next question, why do you use the 3D model to determine the landmarks? Could you just use 2D images to determining those landmarks?
Yeah, we need the landmarks in 3D. So the algorithm was trained on 3D models. I'm not entirely sure if it's going to be very possible to return 3D because I need the landmarks of the ribcage in 3D space. I'm not entirely sure if it would be possible to train a network that just based on a 2D image will be able to predict the depth of the patient and then figure out where these landmarks are going to be. Does that make sense?
Yeah.
You could potentially use a 2D image to get 2D landmarks, but we need 3D landmarks. Also, this is a model that's been developed by Siemens. It's actually called the Darwin model. So you can look up on that. It's really cool. They can return whatever landmarks you ask them to. They obviously would have to retrain everything, but it's still really cool. They've done some really cool work.
Great, thank you. So now we have great comments on interesting work. And this is obviously a multifaceted problem with many different technical angles. In your opinion, what do you think is the most difficult or impactful unsolved scientific challenge that prevents progress in this area?
I think generalizability of the solution, because once you get into a real world setting, you just have You could have a lot of occlusions that prevents you from actually performing any interventional procedure. The patient could be in a weird pose. The network might fail in this case. I feel like the uncertainty in a lab setting, it's really easy to replicate the work, but I think accounting for all of these uncertainties in a real world scenario is going to be really challenging. Also, just in general, the communication problem between all the different sensors, it's also a big challenge. Understanding and analyzing the images. I also find it particularly hard to extend some of the work into clinical settings because of the lack of data, lack of labeled data. It's like, for example, I have never seen an actual ultrasound image of a hemorrhage. I can look them up online, but I don't have access to that data. I don't even have access to a CT scan of a trauma patient. And we can file IRBs and get that, but somebody has to actually sit down and then look at everything, and clinicians would need to segment everything for you, which is generally really challenging. But I think for now is just all the uncertainty and accounting for all the variations that could potentially occur in a real life setting is challenging. And then even having a robot identify when it cannot deal with a situation is also challenging. I'm okay if the robot cannot help this specific patient, but I want it to tell me that, hey, I can't do anything here because I don't know what's going on, rather than think that, feel confident about performing a certain interventional procedure when really it's not a feasible thing to do.
Okay, great. Thank you so much. So we have another question. With the CT scan, how long does the device need to be in contact with the person to get an image?
So the CT scan does not require any contact with the person, if that's the question. The CT scan is just a source and a detector. It depends on the CT scanner, but recently, the most recent ones, they just rotate about the patient, and what they do, they collect a bunch of 2D X-ray images around the patient, and then there's something called the radon transform that allows the reconstruction of the 2D X-ray images into a 3D volume. So I get CT scans from the clinician, and then I can technically segment whatever data I want. It's really interesting to see how you can match 2D ultrasound images to CT scan, but it's a very complicated task. That was a very tangential comment. Yeah. But yeah, CT scans do not get in contact with the person to get an image volume.
Okay.
It's also really bad because it has a lot of ionizing radiation. You can do it a couple of times, but this is really not something you want to keep doing. So.
Great. Okay, thank you so much.
Yeah. Okay.
Okay,
it's really so as soon as you're in contact with the patient, it's like real time. You get in contact with the patient, you get an ultrasound image. It's really easy. It's super fast. And then we collect scans. We collect ultrasound images. I personally collect them at a rate of 1 image per half a second, because that's enough for me to do the reconstruction of the artery, because the robot is super slow. And I make it go slow because, just being a little bit careful.
Okay, perfect. Any other questions from the audience? Great job. So I have just one quick question. So for the autonomous robotic diagnostic system that you discussed, so can that be used for pediatric patients?
Yes. So the system itself can be used for a lot of different applications because it's really versatile. It allows you to collect ultrasound images of whatever you really want. The bigger question is, how do you integrate for autonomous operation? How do you integrate a specific workflow to collect images of whatever you need to collect? So when you say for pediatric usage, could you be more specific as to what application are you looking at? Because even for pediatrics, if you're looking at trauma, you can use the ultrasound system for, visual, for ultrasounding a kid. There's not a problem associated with that. It's more so, what do you want to image?
Yeah, I was referred to the trauma case. So I was wondering about the deep regression network, how now.
Yeah, so Siemens have trained their network, I believe, on kids as well. So that part will work. However, what could potentially fail is the force displacement feedback profile,
Mhm.
because the ribs are a lot smaller and they're a lot closer. So I don't even know if the ultrasound probe can get in between. That's something potentially to consider. So yeah, that aspect, I'm not entirely sure if it's gonna practically work out with an ultrasound probe, but really that was just a workaround because we don't have ultrasound images to use to process that. That's like the next stage is to actually use image guidance for collecting the data.
Okay, great. Thank you so much.
Yeah, thank you for the awesome questions. And if anybody has anything else, just feel free to email me. I'll be happy to continue the conversation.
Oh, perfect. So yeah, we thank our speaker once again, even if we are in a virtual environment, where it is a cheering moment for everybody. And with that, so the speakers will be available in the next minutes for follow-up questions if anybody would like to jump in and ask some questions to them. But thank you everybody for attending today's session. And we'll see you next week for our last speaker of the session. Thank you all.